Hello friends, welcome back to the Dr. Tristos channel. I'm your host, Dr. Tristos, and we wanted to continue with our demonstration program from where we left off. And if you'll remember, we made a new macro called pump, which will output our screen, output a block of text. You can see here. It will output the block up until the terminating code that we define here. In this case, I have ETX, which is end of text, and ASCII 03. And that all looks really great. But you know, the boss came in, the guy, you know, we love him, but he's always coming in here pressing us to make things better. And if you remember in our last example, we proved that by changing this 0 to say UART0 or UART1, let's go ahead and run the code, that we output to either UART. And we proved that by, in this text, we actually say UART0. When we print UART0 over here, you notice it is this block of text. In the second example, we say UART1, and we print screen 1. And if we look here, it says UART1. Well, if we go over to our debugger and switch to UART1, what do you know? There it is. And it's stating that it's UART1. So this was used to test out, make sure our code was working correctly, and it is. So we can take that out of there now. We don't need two different to send our message to two different. But you know, we were looking at this, and the boss came in, and he's like, wow, this pump macro is really neat. And so is the test transmitter ready. You know, all the programmers in the whole company are using those macros now that we developed. And some people are copying them, and some are exchanging the macro we wrote with an email, and they're sharing it, and they're having a great time. Some people have to type it in again because they just see a video, a picture of it, and we're like, you know, that's. Sometimes they make mistakes. Sometimes they don't get it typed in correctly, and even worse, sometimes people decide to modify the macro themselves. And the problem with that is then we have one macro name and multiple ways that may work. So we decided that we're going to distribute these macros to everybody in the company to use. And, you know, it's a great idea. My programming will be in a little bit of everybody's program. That made me happy, so I said, sure, I'll work you up a macro file to distribute. You know, we see this in other languages. You take C, you have different libraries you include that handles different parts of hardware or math functions, etc. You have the same thing in, for example, Python. You include RS-232 libraries, etc. So in assembly language, a lot of times we include macro libraries. So if we're going to share them all, they will go in their own private file. Okay, that makes sense. And so we go in, and here's our macros. We just go in and we snag this. So what we want to do, well, let's just cut them. Now they're on our clipboard, as you know. And you'll just have to take my word for it. But I already created a notepad file called My Macros. It has nothing in it. But let's go ahead and, now there we copy and paste, or cut and pasted our macros over to this file. They all look, they look correct. We can always clean them up a little bit, but they look correct. They look just like the way we developed them in our program, and we want to check these out, make sure they're working okay, and verify once we get them in this My Macro file that they still perform the same way that they did before. So I'm going to close that, which will save it. You just have to take my word for it that I already called it My Macros. You can see here at the top left corner, the file name is My Macros. We saved it. So how is this program going to know about the file My Macros? I've already put a statement in at the top. It's been commented out. We're going to take the comment out, and it says include. And if we read this, include from here, there's a period. So here, you should find a subfolder called includes. And in that subfolder should be a file called mymacros.s. Okay, so a period, backslash, includes, backslash mymacros. Okay, so the period tells it here, where we're at now, right? And where are we at? We are in our, if you remember, I made a folder off the desktop called ZDS, where we could do our projects. And if we go over here to desktop ZDS, we can see that, well, here's our project. As a matter of fact, there's our source code, demo.s, source code. Here is the one with the Zilog logo on the icon is the project, is ZDS project file that describes our project and tells the development system about our project. Debug, if you'll recall, is where our output code is going, our listing load module, object modules, etc. So if we go in, it includes, look right here, My Macros. We already have one. You notice there's some other folders in here, files in here too. And we'll cover them right now. But right here is My Macros. If I open that up, we'll see these macros I just put in. So, you know, since I got the include statement in there, this should still compile and run. Let's make sure that we don't have any syntax errors. We need to switch to UART 0, because if you'll recall, we took out, so there we go. It's already running, sent the message out UART 0. But then we have these equates up here. And there again, the old man that runs the shop says, you know what, this is a duplication of effort. All my programmers, the UART transmitter holding register, the UART line status register, carriage returns, end of text codes, etc. That's going to be common in all of our modules. So why do I want programmers sitting around typing all these labels in, maybe making typographical errors? And remember, we've covered here before, you can make a typographical error in this label that it will still assemble, and you might spend months trying to find the problem. When my early days starting out, I worked with a programmer who was very well experienced, and he had a mistake in the code where it left off a comma 7, and this was on a code that was similar to the IBM 360s, 370 type computers. Only this was on a Sigma 5s, which was built by Xerox, full 32-bit computers. When you assembled the code, it wanted an index register on one of the statements. And if you left the index register off, it assumed register 0. So if you didn't put any register at all, it would just automatically fill that in with register 0. My friend had accidentally left off, his name was Fred Haas, and he had actually accidentally left off, or somewhere during editing, a .7 for the index register had disappeared. The code would assemble fine and run. You're flying the flight simulator, and every once in a while, things would really just kind of go haywire. And there was no rhyme or reason to it. It would become uncontrollable, and then it might go back to normal. And what would happen is when you entered this subroutine, since it should be registered, when you went into the submarine, when you went into the subroutine, it would index into a table of, it was actually barometric pressures, and should have been a .7, so it was using register 7 as the index, but he didn't have, the .7 was missing, so now it assembled, no errors, nothing. Everything looks fine, but you're indexing off register 0. Sometimes when the subroutine entered, there would be some reasonable value in 0, the whatever value it pulled up. The simulator, you couldn't tell. Anyway, it performed well enough that you didn't notice any problems. But other times when it entered into the subroutine, register 0 may have a value in it. What actually we found out happening was it would index it to a place that had a 0 for the barometric pressure. And when it would do a divide by 0, well, computers don't like to divide by 0. And so occasionally it would enter that routine with a value in register 0 that would cause it to index to a place in memory, and it would pick up another 0, and then it would try to divide by that 0. The whole simulator would go nuts. What you had there was, yes, it trapped because it was an illegal instruction operand, and they had primitive recovery type software where what it was doing was trying to recover and continue running. But of course, it was a bad recovery. It took literally a couple of years to find that bug. And we never found it by troubleshooting in some way. The only way we ever found it was we knew that it worked on one version, and then the next version release of the simulator executive program, it no longer worked. So we knew we was fine for years. Suddenly a new release came out that didn't work, and I was pretty confident that there wasn't something wrong with the programming, but there was some other a bug, a typographical, etc. So dear old Fred sat down, and I forget how many tens of thousands. This was on punch cards back then, by the way. I forget how many thousands of punch cards, and he went through them one by one, comparing them to the output listing of the original assembly, until he found it one day. And sure enough, it was an instruction that was indexing to barometric pressure. Everything became obvious when we saw it. My point of all this is, when you're troubleshooting assembler language or you're debugging, it can be complicated, and you may need to use a variety of creative ways of finding the bug, because sometimes your bug will cause the machine to go off the deep end, I like to call it, or the machine just blow up. And problems like that can be hard to define because you destroyed all your diagnostic data. Maybe it wipes out memory when that happens. Okay, so that's another reason why that once we build a library of equates and a library of macros, that it's very important that we test and make sure that these macros are bug-free, or if they do have something that produces an undesired result, we know exactly what that is, and then you can work around it. So if we have these UART equates, well, let's go in the directory. I already put some files in there. And look here, we have ASCII equates. Well, we already have a file that we can share with all the programmers in our company or in our hobby called ASCII equates. And this does the first 33 here, which is mostly control codes, and the last one in the 7-bit values, 127, a delete or rub out, some people call it. So that's great. This file is called equates-ASCII. All right. So let's go back over to our program. And there again, what does all good programmers do? Well, they copy and paste. We copy this statement. And now we call it equates-ASCII. Oops. .s for source file. Did I get that right, or have I got it backwards? Something about it doesn't feel right. Equates-ASCII. So yeah, that looks good. Well, let's assemble it now. We're including this. There again, I copy and pasted because it had the period, which means here. Here you will find a subdirectory called includes, and then that in a file called equates.ascii. So let's see what happens when I now assemble and run that. Yeah, we want to rebuild it. What do you know? Works great, huh? Well, But, so that means I can take these equates out. Oops, sorry. These are the ASCII ones, right? Because I already have them. So now let's see what happens. Oh, that's beautiful. It assembles, it runs, no problem. Oh, that's great. So why could I have equates in this file and then equate the exact same labels again? We did have them right here, remember? And I just took them out. That's because equates won't interfere with anything. You could actually equate to a value, use that equate, then somewhere else in your code equate it to another value and use that label again. So it only happens at assembly time. And remember, the equate is simply going to take the text that you enter after the equate. It's just like copy and paste. It's going to paste that right in. When you use that label, that's the value it's going to paste in the assembly. Okay, so now I have these UART registers. What can we do about them? Well, let's look in our directory, because I already put some folders and files in here today. We have three equate files related to the EZ80. The first one is equates-EZ80. And what this file has, maybe I missed some, but remember I told you that Zilog already uses abbreviations for all of the registers, etc. So we want to stick with those same labels. That way when we're reading a manual or documentation, our label matches what's in the manual. So the first one, equates-Z8EZ80.S. We have two chips, remember, well actually three, the F91, the F92, there's the F93 which we're not supporting yet. But in this EZ80 file, equates-EZ80, these are all the equates that are common to the F91 and the F92. For example, UART1, THR, transmitter holding register. The F91 and the F92 both share the same address for that port, D0. All of these values are in common with both processors, F91 and F92. If you're in this equates-EZ80, then they are common labels that's used in both processors. Okay, so that sounds great. That's exactly what we want. As we always said, copy and paste is our friend, so let's get another copy of that line. And we're going to put it down here. We'll just modify this a little bit. There you go. EC80.S. Okay. So can we take these out? Sure. Because now we're including them from over here in our include file. We're assembling again, and what do you know? Assembles with no errors and runs. But I'm going to show you, not if there's other registers that if we use, the addresses are not going to be correct. So in the F91, if we look, we have quite a few addresses that's not in the common. One of the big differences you'll see is the EMAC. There's a network NIC on the F91. The F92, F93 does not have that. So right off the bat, we have a big range of EMAC addresses. It's on the 91, but you're not going to find them on the 92. So there's other things here. The timers, another big difference between the chips are the timers. Some has more timers, less timers. These are built for control applications. Some people needed more timers, less timers. The addresses for the timers are dependent on the chip. Pulse width, modulation. That's all we need to worry about here for now. Just the point is, the F91 file has equates specific to the F91 chip, and the F92 file has equates specific to the F92. And you can see the big difference here. The F92 is the timers. That's the big switch up here. Otherwise, it uses the same addresses as the F91, which is in our common equates-EZ80. The ones that's in the F91 file, these here, well, a lot of this only exists in the F91. So that's why there's not an equivalency in the F92. The timers is a big one where the addresses have changed. Both chips have timers, and both chips use different addresses. So we're not using any of these registers. Our program that we're dealing with here right now doesn't need to use those equates. We just need our macro file, our ASCII equates, and the common EZ80 equates. Now, I look down here at my macro pump and it's 0, and it just doesn't feel right. There's something about that just doesn't feel right, because who knows? Who likes to call a UART a 0 or a 1, etc.? I mean, it might be better to refer to it as a name. And since 0, we're using it as our console. Let's call it console. And we're going to equate console to 0. And now when I come down here, I can, instead of saying 0 right there, I can just say console. So, looks a lot better, don't it? Pump to the console, my screen 0. We can even take that 0 off there, because now we only have one my screen. So let's make it look even cleaner, and you go, pump to the console, my screen, terminate that pump on an end of text when you run across an end of text. That looks pretty sharp there. Other programmers, my boss had me write up a description of that macro, and in that description I include a copy of the macro so that you can always see the code. We put that in a little manual. Everybody in the company has access to it. They can now use these macros and use these equates because they're in a file. Everybody can use them now. And my code, we added this console equate. All that did for us is the code still works exactly the same, but it makes it more readable. Our assembly language is starting to look like a higher level language. And we all know that a higher level language is always more readable and maintainable. And that facilitates debugging also. So in this video, we've covered the include command and about how we can move equates and macros into separate files. That makes our code here look a lot cleaner, easier to read. But again, I want to stress that building your macros and building your common equate files, I have files that I've used for years. They've never changed. There's no reason for me to change my ASCII equates. The ASCII is not going to change. So once you have a file built and you're confident that the values are the correct values and the labels are the correct names, and you've built macros and the macros are working exactly as you want. You've used them many, many times. You're confident that they're what they do. You can go on and build more powerful macros a lot of times by combining other, smaller macros together. I did want to point out one thing. The boss came in and said, this macro down here, pump, that's really great. But there is times when we don't know what the address of we don't know the label of my screen. If we remember in our macro, one of the first things the macro does is load H&L register pair with my screen. In fact, let's just go here and look at that real quick. My macros So when we invoke the pump command, one of the first thing it does is load the address pair H and L, the register pair H and L with the address of the screen. Well, the boss is saying sometimes we can't do it that way. Sometimes the register already contains the address. When we enter, when you come into my program, the H&L register pair already contains the address. Okay, so, reading up on the manual, I see that instead of using the label my screen, I'll just say H&L right here. H&L already has the value, so what do you think this will do? We'll go look at the output. Let's go ahead and assemble that, run it. This is probably not going to run, because what does H&L have in it? We don't really know, do we? What do you know? We got some garbage, then hello world. It was in a close proximity. H&L must have been in a close proximity. But how do you think the assembly over here handled that? Well, if we go in our library, in our ZDS, go to our debug folder, which has the output. Here's the listing file. That's why this is always important to have your listing and expand the macros so you can see how it assembled. I can't stress that enough for troubleshooting later. So here's where we included the macro file. Then here's where we included our equates file. Here's some more equates. And then here is the data in my screen in the beginning of the app. Remember, right off, we did a no op, then we invoked this macro. Load H&L with H&L. This is a valid Z80 instruction, and it works on the EZ80 also. People may wonder why you would ever do that. This is exactly why. Remember, I told you compilers heavily macro. The output, the pseudo output of a compiler, almost any compiler that you deal with, is heavy in macros. And these macros work together. They were designed as a low-level language, you might say, that the programmer designed. With the macro being developed this way, on the EZ80, I can load H&L with the D and E or the B and C. So back here in our source code, we could have said pump console B and C and end on end of text. That's because this would have compiled here. It said load H&L with the B and C, 16-bit transfer. I don't think you can do that on the Z80, but the EZ80 we can. If you ever hear them talk about optimization phase on compilers, where it optimizes the code and removes redundant instructions and things, if a compiler was to generate this code and it did it this way, and it's just simply a redundant instruction here that's not doing anything, the compiler during the optimization phase would remove that instruction. Now, when you're an assembly language programmer, you really don't want anybody optimizing and removing your instructions, because I may have wrote a program here and, I may know the exact length of this code in bytes because I'm doing a relative jump backwards and I've already counted the bytes, and, I'm not using a label, but I tell it to go backwards 4 bytes, or maybe up here tell it to go forward 14 bytes. Well, if somebody removed an instruction in here, that's going to change that length. You never really want that when you're an assembly language programmer. But this is an example of now, I've got a 2 byte, 2. This compiles. It needs 1 op code, 2 op codes. So 2 bytes but it sure was handy to wasted bytes, but it sure was handy to have this macro. Use the macro every time. It's been debugged. How often do I need to load H&L? Use a register pair on the input instead of. Okay, so what else could we do with that? We could also say, what's the value of example demo? It's 3,000, isn't it? So what if I told down here, what if I took this label, example demo, and here, instead of H&L, I actually said example demo inside of our parenthesis there. I mean, we have this enclosed in. How's that going to assemble? Well, let's look. You will find that it's going to do exactly what you told it to do. And we're going to let this embed in there. It's got 3,000, so there again, it's going to start. Let's go look at our assembler output. We have to open a new one here. Here's our assembler output. Let's come down and look at how that assembled. Pump, and we got example demo inside the parenthesis there. If you look, it made it just like we would as a programmer. The compiler did exactly what we told it to do. Still load H&L, and then it simply filled in the text that we used as an input parameter to the macro. The value of example demo is 3,000. So when it's in parentheses like this, we're going to pick up the contents, memory location 3,000. And it's stored little ending, big ending, so looks like a value of 62 Charlie 3. Is what we're going to pick up there. As we can see here in the assembly, load H&L, little ending, big ending, so 0030, that's address 3000. Here's address 3000. What is the value of example demo? 3000. So it done exactly what we told it to do. And sometimes that can really cause problems, because sometimes we want it to do things that we don't tell it exactly what to do. So one other requirement, what I'm saying is sometimes we don't want it to do exactly what we tell it to do, because we tell it to do the wrong thing. So one other thing came up here. It said, you know what? Sometimes, on occasion, we want to be able to use this instruction. We don't know what is going to terminate the text. We do know, but it's passed to us by maybe the program that calls my subroutine. And someone told me, they said, you know what? The boss told me, he said, we're going to put the value that we want to terminate the printout. We're going to put that in a register C. So, I thought, let me try that. So, as example, we're going to put carriage return. Load register. Let's load register C with a carriage return. Okay. In here, let's tell it C. So how's that going to compile? There again, it's going to do exactly what we tell it to do. And we told it to use a C as one of the inputs to the macro. So now when I come down and I look at our output, from the assembly, it's going to do exactly what we told it to do. Compare down here, it would say etx.asc when we were using that as the input. It now says compare it to register C. Compare C to the accumulator. C has a value of a, I don't know, what we put in there, carriage return or something like that. This works because nowhere else in this code are we using the C register and destroying the value in it. I mean, if we use the B and C register or the C register in this macro or in some code that it calls and we destroy the value, then that's not going to work here. But we can pass values or operands. So that makes our and we see that it printed hello world and ended when it hit the first carriage return. We still have that garbage in the beginning because we said, start at the value of what was in 3000 memory location. So let's go ahead and switch back to our original label. We're still going to terminate on what is in C register. So it should only print one line here. We get hello world. What if we told the register C to load with the end of text and we did it again? I'm running through these different examples. You can see how macros compile and run at assembly time. So now that we go back to ETX, we're going to print out the whole block of text till we come down here and hit ETX. So that we can pass, a register value here, a fixed value, lots of different ways. It's really very versatile. So we'll clean our code up, put it back to where it was at. And that should, now we got a code that runs. We're leaving this off with our code that's running again. We've covered the include statement, more about equates, macros, about passing values into macros, how they assemble, how the assembler treats them. So we're making a lot of progress here. We now have a small library that we're beginning of our includes, which have equates and macro files in them. So we're building our own little library here as we need it. And we have a program that's running. If you have any questions, you can post them in the comments. Or we're on Facebook. You can always go to www.tristos.com. That's www.trsdos.com. I'm sorry this video ran a little longer than I normally like to, but I hope that this was something productive and maybe you found something that would be useful. Many thanks for watching, and I hope to see you back here on the next Dr. Tristos video.